Hey everybody. So we're going to do one more example of using our probability rules. In this case, I'm going to use a little bit of data that I found from, well, you can see the US Census Bureau there. I realize I cut a little too much of it out. This is data about children aged 6 to 17. Okay, and the question in this particular part of the data, they had lots and lots of different bits of data up here. The question in this little bit of the data is about has a child, the percentage of the children in these age groups that had ever repeated a grade. Okay, so we're going to answer some questions. I'm going to make a couple of assumptions. So the children in this study were all identified as male or female. I'm going to assume that there's a 50-50 split. It's not quite that perfect, but it's pretty close to that. And I had trouble finding their exact numbers on that part of the study. So I'm just going to make that assumption for the purpose of making calculations. So let's answer these two questions. Our experiment is, out of all these children that they collected data on, suppose we choose one at random, and then there's two questions. What's the probability the child is a male who has repeated the grade, and what is the probability the child is a female who has repeated the grade? So let's start with that first question. So as usual, I want to define events. So I'm going to use M to be child is male. While we're at it, let's just go ahead and name one for the next question. Child is female. And I'll use R to mean has repeated a grade. Okay, so what we're going to do, let's just start with the first one. As usual, the question, we reform the question using the events that we've written, so that the probability that the child is male who has repeated a grade means what's the probability the child is M and R, and then we apply our multiplication rule, right? And again, if we don't know if the events are independent or dependent, it's always safest to assume they're dependent. And so I use this conditional probability at the end, okay? So now we're simply computing we're multiplying our two values. We're assuming again that half the population of children that were studied are male. And the percentage of them that had repeated a grade out of the males is this 8.9%, so 0.089, which gives us, let's see, let's round this to 0.0045. That seems good. And we can do a similar question, F and R, and then we have the probability of F times the probability of R given F. So in this case, again, we're assuming the 0.5, and we have 0.062. Looks like I have too many zeros up here. I think yeah, I see what I did. Sorry, one of these zeros should be missing. I'll correct that in a second. So this should be 0.031. Let me correct this. Let's see if this works. Oops. Just squishing it. There we go. Oh, that's fun. Okay. So there's our fairly straightforward problem, just multiplying. Again, we're using these, we're using our, there we go, using our multiplication rule to complete this problem. Okay, all right, let's add one more problem to this. Let's say now I'm going to do a new experiment where I choose two, let's say I'm just choosing among the males. Right. So I'm going to choose two of them. And now the question is, what is the probability they have both repeated a grade? Okay. So let's name events. I'll just do R1 and R2, meaning the first person or the first male child I pick has repeated a grade, and the second male child has repeated a grade. So I'm going to do probability R1 and R2. And again, we will apply our multiplication rule. All right, so what's the probability that the first male I chose missed a grade, repeated a grade? We have 0.089 for 8.9%. What's the probability that the second child did? Now, I'm going to just go ahead and use the 8.9% again, and then talk about why I get to do that, because some of you may be noticing that it's not exactly correct to do that depending on how I do this experiment. So I multiply these two together. I get approximately 0.0079. Okay. So a question you might ask is, I seem to kind of ignore this conditional probability here, right? If I've chosen a child the first time, that means if I'm not replacing them, let's assume I'm not, like the same person can't get chosen twice. Let's assume that's the case. Then shouldn't that change the percentage that are left? Like if I had 100 students or 100 males and 9 of them repeated the grade and I picked one the first time that repeated the grade, there'd only be 8 left out of 99, which is not the same percentage as 9 out of 100. That is absolutely correct. However, when we see problems like this where we're dealing with a huge, huge population, we get to ignore that. And here's why. There are something like 24 million boys this age. So pulling one out of there, let's just divide 1 by 24 million. Is approximately 0.000000042, okay, approximately. It does change the percentage, but when you're dealing with this many, 1 out of 24 million is barely noticeable. And even going to 4 decimal places as I did here, this change won't matter at all. So when we see those kinds of things like all people have this characteristic and we're choosing one, we don't have to worry too much about this. It's still nice to write it because it's good to remind us that we don't ignore that, but it won't change our computations, not in a way that's significant to us. Okay, that is it for this video. Thanks everybody. I will see you next time.